Hi, this is Mr. Ferris, and I'm going to walk you through lesson 11.1 on the chi-square goodness of fit test. So here we go. The data that I have already collected from your class includes the day of the week that you were born. So if we were doing this live, I would ask you to raise your hands, but I went ahead and took a random sample. You have to trust me on this. A random sample of 35 students. And these are the observed data that I got. 4 were born on Sunday, 5 Monday, 5 Tuesday, 6 Wednesday, 7 Thursday, 6 Friday, and 2 on Saturday, for a grand total of 35 students. So that would be just the data, and any sort of a categorical problem where you're counting things, counting how many things in a category, whole numbers is what would be expected, then this might be a opportunity to do what's called a chi-square test. So I've collected the data for 7 different categories, and the next thing that you want to look at, of course, is what did we expect exactly? Because, just like a hypothesis test about means or proportions, we should have some sort of a hypothesized value or something that we expect to happen. So unless we have some reason to believe otherwise, I think we would just assume that the distribution, as it says up here, is uniform. That means it's about the same for every category. So of course I picked 35 strategically because that would make us expect 5 in every category if there's really nothing going on. So the null hypothesis, if you would be writing that down, I'm going to squeeze it in here because I didn't really have that much room, but the null hypothesis would be that the distribution, one way we could say it, the distribution of birth days, and I mean that separately, like birthdays of the week, are uniformly distributed. Now, if they were not uniformly distributed, unfortunately, we'd have to write down the percent we expect in every single category. So for 7 categories, that would be kind of tedious. Fortunately, we're expecting a 7th each time. And so you might notice that, we're not the same. Maybe Monday and Tuesday looks like we're good. We got exactly what we would expect, so we're not off at all there. We were a little high on Wednesday and Thursday and Friday, but we were low on Saturday, just a little low on Sunday. So it doesn't look like we're off that bad. But of course, we have to come up with some sort of statistic. And it's not going to be a mean or a proportion exactly. We want to come up with some statistic that would measure the total difference somehow. So we could think of lots of ways to do that. In class, what I'd probably do is give you time to think about the different ways you could come up with some statistic that measures offness. How far off is the distribution of data from the distribution that we expected? So all kinds of ideas would be, you could calculate the differences of all these, and as we learned from some other tests, we would probably do the absolute value maybe of the differences. That would make sure that the differences are all positive, because otherwise, of course, they would just cancel out if you use negatives and be 0 difference. But as you might remember from standard deviation calculations, another way to make sure we have positive differences is to square them. So one way we could, and I kind of got probably too many rows here really if you were doing this for a real problem, but I'm kind of walking you through step by step just because it's the first time through. Why don't we just calculate the difference but keep it positive? So let's do observed minus expected. If you did observed minus expected, you would get -1, 0, 0, 1, 2, 1, -3. But if we squared them, you might remember that there's some algebra that comes into play when you square. So if you square all these differences, you would get these numbers: 1, 0, 0, 1, 4, 1, 9. But of course, now what we've done is we've taken the counts and we've squared them. So now these are like, if we were thinking of the units, these would be like square counts, which doesn't really make sense either. So what we might want to do to get it back into counts is to divide and get it back to the same units. Or another way of thinking of it is, being 9 off or even 3 off, depending how you want to look at this, being 3 off, is that really a lot? Well, if you have a small sample size, no, that's not very, or that's maybe a little bit bigger. It's like 10% off. If this was 3 off out of 350, we'd probably think, that's not really much off at all. In fact, that's pretty close. So offness really is relative to what you expected to get. So for that reason, since we expected to get 5, the offness here is maybe 1 out of 5, or 4 out of 5, or 9 out of 5. The offness is bigger, of course, relative to 5 when you were 9 off. So for that reason, what we're going to do in this last column, we're going to take that same observed minus expected. We take the observed minus expected that we got, and we squared it. Remember, this line here was all squared. And we're going to divide it by what we expected to get what we might call a relative difference, relative to what we expected, which seems to be a more fair way to compare. So if we take 1 divided by expected, and 0 divided by expected, and 0 divided by expected, and 1 divided by expected, if we divide by the expected the entire time all the way across, these are all of the relative offnesses, if I can use a word that doesn't exist. This is relatively how far off we are relative to what we expected to get. And if you add that all up, you get the statistic that we believe is important and is a way to measure the entire offness or the aggregate offness or the offness of the entire distribution. So this number, which I have calculated elsewhere to be 3.2, is the total offness that this data is from what we expected. Once again, relative to what? Is 3.2, that's not standard deviations. If it was standard deviations in a normal model, we'd think, ooh, that's way far off. But that's just how many of these statistics, this is a new statistic, a little more complicated than a mean or a proportion, but this is a statistic, and this statistic is called the chi-square. Chi is it looks like a capital X in the Greek alphabet. Capital X, it's kind of a script, capital X is called chi. It's not chai or chi, it's spelled C-H-I, but it's not chai or chi, it's just like kayak. Think about kayak. This is chi-squared. This statistic has a distribution, just like X bar has a distribution, P hat has a distribution. And if you did this over and over and over, took another sample of 35 students and calculated this, take another sample of 35 students and calculate this, take another sample of 35 and calculate this, these chi-squared numbers will be piling up just like we were doing with means and proportions. And strangely enough, if you would imagine this distribution having, and again, if we were in class, I would say, all right, discuss this. What do you suppose this distribution would look like in the long run if a bunch of these chi-squareds piled up, taking more and more and more samples of 35 until you took every possible sample of 35 from Noblesville High School and did the same thing? What would these chi-squares look like? Well, when you think about it, there's a number over here that you can never, ever get less than. When you think about how this was calculated, we're calculating how far off we are from what we expected. Well, the least possible amount that we would be off, if you think about it, think real quick. Think about the least possible offness that we could be. Well, we could have hit 5, 5, 5, 5, 5, 5, 5. If we'd have done that, the total offness would have been 0. So there's no way this distribution can get lower than 0. In fact, rarely would you ever get 0. It's usually going to be a little bit off from that. But you could get some weird sample that's way off. And so you can't get any further left, but you could get pretty far to the right. So maybe if you can imagine this, you can't go further to the left than 0, but you could get way far off to the right every once in a while. Not very often, but every once in a while get a chi-squared number that's way off. So this is going to have to be skewed right. I don't have enough paper to show this, but this will be a skewed right distribution. And so offness is going to depend on what the scale is. I mean, what is the scale? Is it 1, 2, 3, 4, 5, or is it 2, 4, 6, 8, 10, or is it 10, 20, 30, 40, 50? What we want to try to figure out is what's the probability that we would get this far off or even farther. Does that sound like something we're supposed to know? What's the probability we'd be this far or farther if this is really what's going on, if there's really no difference? So let me show you, let me fill in some blanks here. The chi-square statistic, if you think about what we did, is we calculated this statistic for every one of the 7 categories, and then we added them all up. And so if you think about what the formula would be, it was the observed minus the expected counts squared. We did that in the 4th row. And then we divided by the expected counts, and that's how we got our 3.2 number. That statistic is called the chi-square statistic, and we can calculate the p-value for that. 3.2 ends up being kind of like right there. 3.2 is not even halfway over. And so the p-value for this, not real sure where to put that. Let me stick it right here because I forgot to write the alternative. The p-value ends up being 0.78. So the chi-square statistic was 3.2. That turns out to be not very far away from 0. And therefore, since the p-value is so high, of course, you know what to do with that. We would not reject the null. We have no evidence that our distribution of birthday days of the week is any different than just uniform. We're off a little bit, but not that much. What I forgot to write earlier was the alternative hypothesis. The alternative hypothesis is that at least, if you think about this, it should make sense, at least 2 days of the week are not uniform. If you think about it, if one day is off, there has to be another one. So if one day is higher than we expected, well, there's got to be another day at least one that's lower than expected. So we kind of write that in that way, that at least 2 of those categories are not what we expected. They're not uniform. And then we do have some conditions. I'm going to write these here, even though the question is for something else, because I just want to get this on the paper. There are conditions, and you can imagine what the first one is. Because this was a sample, you want to make sure that a random sample was taken. And I can assure you, I did that. I did that with my calculator. I did a random integer 1 to 70 without repeats, and I got a random sample of students. Because this is a sample, we also have to check the 10% condition. Here's where we have a little bit of a problem. Because we only have 70 students, AP Stat students, so I took a random sample that was half of the class, half of all 3 classes. So we violated the 10% condition. So 35 is not less than 10% of the population. So we violated a condition, but we're going to continue just because I needed a good example. And in real life, we'd say, okay, we got to either probably what we'd have to do is go out and pretend our population was all of Noblesville High School and take a sample of 35 from the entire population, or from the sophomore class, or out of all AP students, or something like that. We'd have to get a bigger population. So we know we're violating that, but I'm using this as an example, and ordinarily I think that would typically be met. And then, as you might guess, I mean, these are the same kind of conditions we've had before. You have to have a good sample. It can't be too big, but it's got to be big enough. So this is going to come down to the expected counts. The expected counts must be at least 5. Of course, I picked that strategically so that I would have exactly 5 in all of them. Just make sure that the condition you check is always about the expected counts. Well, the counts that we actually got, of course, we had a couple that violated that, 2 and 4. But it's not about what we did get, it's about what we would expect to get. So make sure you check that condition for the expected counts only. So then we can proceed with what's called a chi-squared goodness of fit test. It's kind of a strange test name. And maybe the grammar actually isn't the greatest either, but what we're trying to do is we're trying to see how good, or an English teacher would tell you, how well does our data fit what's expected. And in this case, I guess you could say it, it fits it fairly well. We had no reason to believe it was different than uniform. And if we were doing a step 4, we know what to do with a high p-value. We would again use alpha of 5% and say something like, because our p-value is greater than alpha at 5%, we would not reject the null hypothesis. We have no evidence to believe that our distribution of birthday days of the week is any different than what we would expect, which in our case would be just uniform. So there you go. Those are the steps of a chi-square goodness of fit test. Some things are very similar to what we've done, but of course the distribution is a little different and our calculations are a little different. And when you get onto a graphing calculator, this is also where it gets a little different. What I can show you with my TI-84, this is the one that I use in class. You should recognize that. That calculator, if you go to Stat and go over to Tests and go down to the bottom, you'll see there are two, at least with the new operating system, there are two chi-square tests. There's a regular chi-square test, which is option C, and then there is a chi-squared GoF, or goodness of fit test. So we can, if you have a newer calculator, you can do a goodness of fit test using lists. But when you click on it, you'll notice you will have to have all your observed counts sitting in list 1, and you have to calculate and write down all of your expected counts in list 2. So in my case, what I did was I put the top row, 455, 6762, put those in list 1. And then I put 555, 555, 5 in list 2. And I had the right degrees of freedom, which I didn't write that down either. The degrees of freedom is always n minus 1, but n is defined not as 35, but n now stands for the number of categories that you have. So we had 7 categories. So for our goodness of fit test, we would have entered 6. So 7 categories minus 1 would be 6 degrees of freedom. That's what we would do, assuming our data is in there correctly and you calculated it. The calculator would come out with your test statistic, 3.2, and the p-value, 0.78. And those are the two numbers, of course, you need to get full credit for step 3 in a goodness of fit test. So I think I covered all the pieces, not necessarily in order, but those are all the pieces to a chi-square goodness of fit test. So what I would ask you to do is to complete Mendel's P's. First thing, of course, you want to do is you'll need to find your sample size, which I believe was, I think it was 556 if I remember correctly. Yeah, 556. You're going to need the total number so that you can take, if you've had any biology, you know that there is a theory about the genetics ratios. So you'd have to take 9/16 of 556 and write it there, 3/16 of 556 and write it there. You got to take these fractions of 556 and write them here. And these most likely will not be whole numbers. Those are going to be decimals. And then the chi-squared number would be the bottom row like we did here. You would do observed minus expected squared over expected, and you would write those in here. And then when you add these all up, that will give you the total chi-squared number for the entire problem. And then at some point you'll probably use list 1 and list 2 and your nice shortcut on your calculator to get the chi-square test statistic and the p-value and just verify that your calculations are correct. So you would want to complete that secondly, and then on the next page there's an opportunity for you to do a chi-square test on M&Ms. And if I was in class, I would have a big bag and I would actually take a sample and we would test our sample compared to what is supposed to be in there. And I don't know if you knew this or not, but there's 2 factories that make plain M&Ms. There's, I think it's Hoboken, New Jersey maybe, and then Cleveland, Tennessee. And those 2 companies have different distribution percentages. And if you look on the back of the bag, somewhere on the back of the bag, you'll see this little code, and that will tell you which factory your M&Ms came from, and so which expected distribution you should use for your bag of M&Ms. So if you have a bag of M&Ms, you could do a chi-squared goodness of fit test to see if whether or not you think the distribution of colors is as the M&M's company claims. So that would be another practice problem that would be good for you to do. The downside here, of course, is everybody will have a different bag, so it's a little hard to check our answers. So it would be nice if you could get with somebody else and do the same bag maybe. So at this point, I'm going to wrap up the video. Hopefully that's enough to get you started. You definitely want to do some practice problems and be ready for the quiz coming up over the same stuff. As always, let me know if you have questions. Email me, and I'll try to get back to you as soon as I can. Good luck.